Hi, I'm Roman Maeder, Director of Parallel Computing Technology at Wolfram Research. I will talk about persistence and initialization. I will show the new 11.2 features for storing information at various locations and how to use it for kernel initialization. Okay, good afternoon. I'd like to present you some new things you can do with your enterprise private cloud. We brought parallelism to the private cloud environment. And so I'll show you some technical issues there and discuss the licensing options, what you actually need to use it inside your own organization. So we have a new thing called HPC Accelerator for private cloud. It hasn't been officially released yet, so this is kind of a preview because we are still figuring out some of the details, but technically it's ready and I can give you a demo today. So it supports parallel computing in the same way that you do parallel computing on the desktop. So the idea is that it should be the same experience. And what this requires is some extra software in the cloud kernels to allow launching subkernels for parallel computing. And of course, licensing options for those parallel subkernels. And the idea is that it looks the same, as with the desktop. So how does parallel computing look on the desktop? So the way you use it, you launch some subkernels. Here I launch 4 kernels on my local machine. Then I do some parallel computation. I have here a command that takes the numbers from 1 to 500 and selects those where 2 to the nth prime minus 1 is itself a prime. This now happens in parallel on those 4 kernels, and when you are done, you close those kernels. And in the cloud, you have a similar experience, except that you don't use the mathematical front end, but you use your web browser, but the screen will look exactly the same. You will see it in a couple of minutes. And technically, what's happening is inside your PC or workstation, you have a couple of open windows with notebook documents that are connected to the mathematical front end. The front end is connected to the session kernel. That's the kernel that does your computations. If you type 2 plus 2 in this notebook, that gets sent to the session kernel, and the reply 4 goes back to the notebook. And usually all the notebooks are connected to a single session kernel, although you could have more than one session kernels. And parallel tools allows you to launch subkernels connected to these session kernels. What I showed you were local subkernels which run on the same machine where the session kernel runs. But if you have additional hardware, you can also launch subkernels on any available remote machines here called nodes, typically nodes in a cluster in a high-performance environment. So you will have to make a call to log into those machines, launch the kernels, and then make a connection. And all of this is supported by the parallel tools, which allow you to set up the configuration of which kernels you want to use. In the cloud, we support the same 2 models, local and remote subkernels, but you have to make up your mind what you want, because in the cloud we have to restrict what users can do, because it's a shared environment, so you cannot just do all kinds of funny stuff. Here is the situation where you have local kernels in the cloud. So the cloudy thing here is your private cloud. There's a big web server there that services all the requests, and you can access it from anywhere in a web browser or on a mobile device. Now in a cloud, there are typical several session kernels. Each user notebook here has its own session kernel. And the idea now is that from that session kernel, you can now launch subkernels. So this user will use 3 subkernels, and this user here, one of those, would in this case use 6 subkernels. But all those subkernels run on the same machine where the cloud itself runs. And this cloud machine is typically a virtual machine. That's what you get if you buy the private cloud. You get a virtual machine image. Then you have to find some hardware in your organization where you can run this. Now, this is of course limited because, I mean, that machine is always also serving the cloud, so it's probably doesn't have a lot of additional resources. So you cannot do hundreds of kernels in this way. If you want to do hundreds of kernels, you have to provide your own hardware for doing so. So the picture then is similar as before. The private cloud, your notebooks are connected to a session kernel, and the session kernel then makes connections to any of the available remote compute nodes. And in this way, you can scale it to hundreds of kernels. Now, what are the technical requirements? If you want to do what we call the localhost parallelism, where the subkernels run on the same machine where the private cloud runs, you need enough compute cores. Now, these are virtual compute cores because it's a virtual machine, so this only works if there are hardware cores in the background that actually support these computations. And you need these in addition to those compute cores that support the private cloud itself. Now, the private cloud is highly configurable, so you can decide how many kernels you want to provide for the cloud itself and how many you want to provide for doing parallel computation. And as maybe you have seen it yesterday in Stephen Wolfram's presentation, where he showed how the private cloud is configured. When you get the private cloud, you open a Mathematica notebook that contains all the parameters for setting up the private cloud. And there is a new such parameter that's called parallel computing, and it allows you to turn on and off parallel computing. And if you want to do computing on the same node as the private cloud itself, you would set the compute nodes to localhost, and you can here specify how many kernels are allowed for parallel computing. Then you generate a new configuration for your parallel cloud, and then it will support parallel computing. Now, for cluster parallelism, where the parallel kernels run on different hardware, you need to provide a few more things. Obviously, you need to provide the hardware, a cluster or a rack full of machines that are capable of running the Wolfram engine. The Wolfram engine is a Mathematica installation without the front-end documentation, things you do not need in this environment. You need a network between the private cloud node and those compute nodes. It should be as fast as possible because that network will be the bottleneck for the parallel computation, because all the communication goes between the private cloud and those compute nodes. And you need licenses for the compute nodes. We do have special licenses for parallel computation that are part of the old Grid Mathematica, which is still supported. I mean, Grid Mathematica is doing parallel computation from your desktop. And here instead of from your desktop, you do it from the private cloud, but the backend, the compute nodes are the same. So we can use the same licensing schemes as we use for Grid Mathematica. And to configure your parallel cloud like this, you would actually list the compute nodes here in the private cloud configuration, the number of kernels per node. And if there are more than one network interfaces, then you may have to specify the local endpoint of those computation, but normally this is not necessary.
Roman, is that
yes.
That previous expression for the parallel compute nodes, is that supposed to be a list, or is it just
the configuration language is based on JSON. And so it's a comma-separated thing of node names. Yes, I mean, it's not standard. I mean, but that's why we provide the example right in the notebook, so you know what you have to do. And this then turns into a list of host names inside your session kernel. Now you need to do one more thing. Obviously, you need to set up these compute nodes so that they allow login from the private cloud. And this is not something we can provide because we don't know what environment you have, and we want to support as many environments as possible. Therefore, we simply state the requirements, and your local system administrator will then have to set up those compute nodes. So you need compute nodes that support running the Wolfram engine and support logging into, which in practice means one of the standard Linux distributions and the Wolfram engine installed. Then you need to set up a login name that the cloud can use to reach those compute nodes. And you need the Wolfram engine installed, preferably on a local disk and not on a network disk. If you have 100 compute nodes and all of them launch 8 kernels, that means 800 process starts at the same time. And if that Wolfram engine installation is on a shared disk, that server will break down at this point. And so it's quite easy, just put one copy of the Wolfram engine onto each compute node, and then they will not have any bottleneck when they launched. And the last requirement is a fast network between these nodes. Now the communication to launch the kernels from the private cloud to the compute nodes goes with SSH. And in the private cloud, there is a username under which the cloud runs. And so you need to allow this user to make SSH connections into your compute nodes. And this is very easy to do. You just create an SSH public-private key pair. The public key has to go into all the compute nodes, which then allows the head node, which has the private key, to log into those compute nodes. We provide, when you set up the private cloud, you can log into that private cloud yourself as the system administrator and just copy the key pairs in place. And the network must allow for these SSH connections and the backward TCP connections for the kernel connections. Now, if it's on the same network, that's not the problem. If there are firewalls and NAT routers in between, then you will have to do a little bit of configuration there. But we assume that this all is inside a protected environment, so you don't need to put additional problems between the virtual node, private cloud, and the compute nodes. So the security is outside, and then you can freely connect between those nodes. I should give you a quick demonstration at this point. We have set up, it refuses to quit full screen mode here. I don't know what this button doesn't. I'm stuck in full screen mode, so there's probably magic. I have a link, let me see. Okay, now, so this is my web browser, and it's connected to that internal test cluster. The test cluster consists of a head node running a private cloud and 2 compute nodes with 4 cores each. And in that private cloud, I have another copy of this presentation notebook. And so what you see here is not the mathematical front end, but it's the web browser inside being driven by the private cloud. So you can, of course, do any kind of evaluations, but more importantly, you can do parallel computation. So what I'm doing here is now running in the private cloud. So I'm connected with the web browser to the private cloud, and the private cloud has a session kernel reserved for me where these evaluations happen. And I have the same idea. I can do launch kernels, and it will now launch the pre-configured set of kernels for me to use. Here is some information. So I have the node name. So there are 2 nodes and 4 processes on each of those, and that's the username under which this is all running. And then I can do now the same kind of parallel computation as before. I mean, there's really no point in giving a long demo because the parallel computing is exactly the same now on the private cloud as on the desktop. I mean, that's the whole point of the exercise, that we bring you the familiar parallel computing experience into the cloud. So what is now, of course, more important than on desktop is when you're finished with your computation, you should close those kernels because somebody else might want to do parallel computing. And if 2 people launch each 8 kernels, then there are more kernels running than there are actual cores, and so you will not see the speed up that you expect. So that's really all there is to demo. I mean, there is nothing new. On purpose, we try to make it. So this is the situation that I just demoed. I have connected from my browser to a session kernel, and the session kernel has launched 4 subkernels on 2 nodes. And the setup was done exactly like this. We have an SSH key in the private cloud. And there's another technical requirement. The kernels in the private cloud do not allow arbitrary connections to the outside. They run in a sandbox. And so we have a version of that remote kernel launcher that interfaces with the sandbox. So you can make connections to that pre-configured set of remote nodes. It also means the cloud is protected against users trying to make connections somewhere else. So the configuration is outside the user session kernel. So you cannot bypass those restrictions. Now, of course, the question is, as I said before, if 2 people at the same time try to run the full set of kernels, then you might not have the experience you would like to have. So what happens is the following. The default configuration in the cloud is to use the full set of kernels. But you can actually decide to use fewer than those kernels available. Now, on the localhost parallelism, when you say launch kernels, when you do not give an argument here, it will use the default. But you can say, I want to use only 2. And so 2 more are available for somebody else. And in the case of using external compute nodes, it looks a little bit more complicated, but the idea is the same. You can specify a subset of those nodes that are available and say, I want to launch 2 kernels only on each of these 2 nodes. And then I can just create my own configuration. Or you could even have your system administrator provide certain configurations, not just the default configuration, but some other ones that you can then reference by name. And so you could have a small configuration for doing testing, and you could have a full configuration which gives you everything there is for doing the actual productive run. So you are not restricted to you always using the full set of kernels, but you can actually decide to use only a smaller subset of those. Now, of course, that doesn't really solve the problem yet, because it's still a question of using the resource, a shared resource, so that you get past each other. I mean, that's also the reason why this technology does not exist in the public cloud. In the public cloud, we cannot assume that we have only nice users that will obey any restrictions that are company policy, but we'll have people from all over the place who will just for fun try to run 100 kernels each. And so this kind of private cloud parallelism only works in a cooperative environment. And so it is up to your organization to put up guidelines, say, maybe, okay, in the morning I use 100 kernels, in the afternoon somebody else uses 100 kernels, or I have smaller configurations where I can do debugging with 2 or 4 kernels, and then when I'm ready to do the full computation, then I will reserve the machine for me for a certain time. We do not provide a software solution for doing this reservation. We don't have a full reservation system. At this time, we assume that this is a cooperative environment where you can talk to each other and decide who gets to use the machine at what time. Of course, this is open to further development. Maybe at some point we will be asked to provide a reservation system, a job scheduling system. You may be familiar with some of these job scheduling systems that exist for supercomputers and so on, and we might do the same. But at the moment, we on purpose did not do this. We provide the tools, and your organization will have to do the scheduling of the resources. It is also the case that if you stop using a session kernel, then the session kernel will time out. And when the session kernel that has some subkernels attached times out, the subkernels will quit automatically. So you do not get hundreds of rogue kernels lying around. It takes care of itself, and it will only keep them alive as long as the session kernel is still being used. So how do you actually get to use this? In the future, every private cloud will support the configuration for parallelism. So what I showed you at the beginning, you can open the configuration notebook for your private cloud. You can enable parallelism. There's no extra charge for this. But of course, to actually use it, you need licenses for these kernels. And in the case of cluster parallelism, you need to configure that additional hardware and SSH setup. And of course, private clouds are typically sold with a service support contract. So this support for setting up the SSH and the compute nodes might be part of that service contract for the private cloud. So if you are interested, if you are a current private cloud customer and would like to use that, or if you are interested in the private cloud itself, just talk to us and we can tell you what the possibilities are. There's another way we could provide this technology, and that is a question to you, whether you are interested in this. It would be possible to have to set up pre-configured images, for example, for Amazon EC2, that include the private cloud plus a set of compute nodes. And then you could obtain that image. I think there's just an hourly charge for using it for a certain time, and it would be pre-configured. So you could log into the private cloud on that Amazon instance and use, say, 200 compute kernels within that instance. That would be another way of providing that technology. Would have the advantage you don't have to buy your own hardware, you just rent the Amazon system part of it for a certain amount of time. I mean, that's particularly interesting if you don't use that in continuous mode, but have maybe a need to do something for 1 or 2 weeks, and then the computation stops, and then you can just stop using it, and you will not be billed for it for additional time. Okay, thank you.